Welcome back. This is our last official lecture. Next week we'll meet at the regular time for final presentations, so everybody needs to have 30 minutes or less to present their final projects. And I'll remind you that the oral presentation is a significant part of the scoring for the class, so it's important to try to make that effective. We'll take some time at the beginning for people who didn't present last week and to present their preliminary projects. We'll get updates from everybody, and then we'll try to finish up the arrow diagram exercises in the in-host viral replication model. As usual, I need to remind you this is being live streamed on YouTube and recorded, so please be aware of that. The other thing I was going to say is that if anybody's interested in trying to understand how these kinds of things work in spatial contexts, I teach E543, 443 next semester, and everything that you've used here would be very useful for that, so you'd be welcome to participate. So again, we're going to first start out with you presenting your material, and then we'll come back where we were. We'll go back over some of the exercises because some people had asked to do those again in a little more detail. And then we'll try to see if we can finish the immune response model. So I'd like to come back to the preliminary NanoHub project presentations. I got only one formal review from people. I know some people who you were supposed to review didn't have material to review, and that made things a little more complicated. So if you can get that done by the end of the week, that would be good. And please contact me if there's a problem in making that happen. And I also didn't get the exercise 12A, the comments on the short comments on presentations from people, either for a number of people. Please do those for this week as well if people are presenting. Again, when you're thinking about people's presentations, you can talk about the topic. In particular, is it clear? Do you find it interesting? Is the biology presented clearly? Is the purpose of the modeling clear? And if it's thought of in an educational context, or the learning objectives of the project clear? And then you can make suggestions, either what worked or what could be improved. The model itself, was the model presented clearly in a way where its assumptions were clear? Was the math presented clearly? Because ultimately these are mathematical models. And do you feel that the model actually demonstrated the things that were being presented? Did it in fact teach effectively? In terms of slides for the oral presentations, how were the slides? Were they clear? Were they sufficiently detailed? How could you make the presentation have more impact? And then for the oral presentation, actually half an hour is not very long to present complex material like this. How did that go? So before we go any further, I'd like to come back now and ask people to update me. For people who presented last week, I'd like to ask for updates. For people who didn't present last week, you have the opportunity to present now. Why don't I start with Benjamin? How are things going, and do you have some material you want to show today? Are you there?
Is this, can you hear me?
Okay, sure.
All right, yeah. So I've done a little bit more work on the on the application, which unfortunately right now still hasn't been it's on the last stage of the process for getting onto NanoHub. So right now that's not online, but the I think probably bigger part is that I now have a PowerPoint presentation about the actual thing for presentation. Um, I'm a little lost on what I should and should or shouldn't be including within the actual oral part of the presentation. So that's I don't know. That's sort of where I'm at.
Well, I mean, ultimately, what you need to do is walk through and teach people how to use the app and explain how you came up with it. And a lot of that material might be in the Jupyter Notebook itself, because the Jupyter Notebooks are meant to be freestanding to some extent. But there may also be material that is relevant to the class that wouldn't be something that you'd put in Jupyter Notebooks. If there were decisions you had to make when you were building the model, or you pulled material from multiple sources and you had to learn how to integrate it, or you had to understand the mathematics or the computing, those are topics that would be of interest to the class, but might not belong in the Jupyter Notebook itself, because the Jupyter Notebook is a finished product, whereas your talk about the Jupyter Notebook is certainly showing people how to use it and explaining it, but also could involve discussion of how you built it and what challenges you faced building it. TJ, do you have any ideas or comments that could be helpful there?
No, I think that sums it up about right.
So I think you could imagine having a split screen where you have a slide deck on the right and the Jupyter Notebook on the left. And the slide deck gives you the background and context. And then you use the demo on the right. Or the slide deck could be separate. You have to decide how you'd like to present that. Again, because you can put text into the Jupyter Notebooks and figures, it's a little bit less, the slides may be a little bit less essential. But in general, there are going to be things that you might want to talk about that wouldn't belong in the notebook itself. Okay, Ali.
Hi, sorry. I'm not like finished with anything, but I have like a presentation I can show, I guess.
That would be great. Let's see what you got.
All right, give me just a sec. Okay, so for my okay, go away. Sorry, I don't. For my final project, I'm modifying Nico's tuberculosis model. Beginning of the presentations is going to be kind of a review because I did already present, I guess, on what his model is trying to achieve, and I don't want to be too redundant. But basically, his model is modeling like the effects of antibiotic treatment, vaccination, and antibiotic resistance on tuberculosis. And so this is the same slide as last time, but just a quick refresh. Tuberculosis is a bacterial infection that typically manifests in the lungs. It spreads through the air, and it's not going to like spread through like, other ways that disease sometimes spread, like saliva or like sharing food and stuff like that. It's going to spread with the air. And it's the second deadliest infectious disease now in the world. Used to be the first one when this was published a year ago, but now COVID-19 has surpassed tuberculosis. A very interesting thing about tuberculosis is that it has a long latency period. So some individuals will just never show symptoms. And a problem with the latency period is that people that are infected and aren't having symptoms, if their immune system becomes compromised in some way, can then start exhibiting symptoms. So people with like HIV and AIDS are more at risk for that. Another issue with tuberculosis is that the treatment plan for it takes a very long time. I think I read it was like 20 months or something. And so there's a kind of a constant problem with people that won't take their treatment for the entirety of the plan of what their doctor told them to. And so then the tuberculosis bacteria can become resistant to antibiotics. Another quick thing is that tuberculosis disease, which is different from tuberculosis infection. Tuberculosis infection just means you have it, but you can also just not be showing symptoms. It progresses in tuberculosis disease when you're actually showing symptoms and you're contagious to people. And then another note, if it is in its latent stage inside of you, you're not going to be contagious to other people around you. But I guess doctors look at the sputum sample from a patient to determine whether or not it's progressed to tuberculosis disease. And sputum is just another word for mucus. So the three, I guess, results of the test is like smear positive, which means that this bacteria was detected in the lungs. Smear negative, which means it wasn't detected. And that doesn't really mean it's not there. It's just not as prevalent, so it doesn't detect it. And then the other result is just non-pulmonary. It's like you're infected by tuberculosis, but it's not in the lungs, which I think is the rare case. It's generally in the lungs, but it can also be in like the eye and such. But yeah, so something I did talk about as much last time is that this project was largely inspired by a paper titled "The Epidemiological Benefits of More Effective Tuberculosis Vaccines, Drugs, and Diagnostics." It basically demonstrated the effects of new treatments and preventive efforts on tuberculosis cases and death. So there's like a table here too. If I can open it, hopefully it leads me to the right place. So this table kind of also shows like the results of the model as well, but you can kind of see on the left the different intervention strategies they've highlighted. So different types of vaccinations, like whether or not it's, being like you're getting vaccinated before you're being exposed or not. Then they also have like different diagnostics, combination of those diagnostics. And then it also explores some other things like, mass vaccination, kind of goes into depth, mass latent therapy, stuff like that. And then on the right are different results from the model that inspired this project. And then this is like the picture of like the flow chart of their natural history model for tuberculosis. So you can see here too, which we'll see in a different second, is a little bit different than Nico's mathematical model. His is more simplified, but here they've separated it to latent fast and latent slow categories. And so people that are receiving vaccines before they're exposed to tuberculosis are going to end up more in this latent slow category versus this latent fast category. And so you can kind of see how there's like different options of how tuberculosis will progress inside of you. So, you know, smear positive, smear negative, or non-preliminary. You can kind of see can result in death. You can recover, but you can also be reinfected after you recover, which is another problem. You can be cured, but then get sick again. So it's kind of annoying in that way. Again, Nico's, the goal of his application was to explore how tuberculosis spreads among a population, accounting for vaccination and antibiotic resistance. And I think after that, I was going to switch over to his model really quick, just so you can see. He has a different, he like expands the mathematical model as he adds on vaccination and antibiotic resistance. But you can kind of see here how this model is just a little bit different than the one that the inspiring paper had. Instead of like having like, I think it was, okay. I think fast versus slow latent period is just divided into one latent period. And then there's the early infected population. And then smear positive, smear negative, and non-preliminary, treated, recovered. So it's kind of like an SIR model, but maybe a little bit more complex. And then there's a bunch of parameters, which you can see here on the left, and the outcomes of that. And then I'll go down really quick and demonstrate. This is the one, vaccines. The only difference here is there's like a V added on. Can you see me circling with my mouse? Okay, cool. And then the antibiotic resistance model is definitely a bit more complicated looking, but this one's basically just counting for resistance. So R here's the recovered population. But you can see up here, it's also accounting for resistance. So we have, I think, resistant latent population, resistant early infected, resistant smear positive, smear negative, and then non-preliminary population, and then resistant treated population. So kind of see it. It seems a bit complicated, but it's basically just the same as what we had before, but we added on the parameter to account for those who have the resistant strain of tuberculosis rather than just the regular strain that will respond well to antibiotics. Let me go back to my presentation. And then, okay. So the goal of my project then, you know, obviously like he's done a great job with his project, but I was really inspired by it and I wanted to expand upon it and like implement some of the improvements I talked about last time, as well as some other ones that I've discussed with both Professor Glazier and Nico himself. So the goal of my project basically is to improve the application and the model, verify its results, and provide additional insight to the project. And so the main, you know, improvements and additions that I'm going to try to work on is the first one is just to explore the results when the mathematical model is altered such that smear positive, smear negative, and the non-preliminary categories filter into 3 different treatment groups. So right now, I'll scroll back up here. You can kind of see that these 3 all shift into one treatment group. And so something that Nico actually brought up himself when we met was that he would like to see, I think, what would happen or how the model would be changed if each one of these had their own treatment category. And so that might be something I try to do. Next thing I want to do is elaborate more on the mathematical model in the application and break it down into comprehensive steps. I just kind of took that from a standpoint of assuming the audience is like, needs it dumbed down a little bit. So, you know, I just wanted to like kind of take certain clips of it or just like provide a more thorough explanation of the mathematical model for those who aren't as fluent in, you know, the math and reading diagrams. So that's kind of self-explanatory, I think. And then in addition to that, I wanted to provide a bit more biological background. He did provide, like, he did a well, like, providing biological background in the paper, but I wanted to incorporate a little bit more just so people are comprehending everything. I will mention though, I also found out that you can like link to the NanoHub application was like his final paper, and it definitely did go more in depth than the model did sometimes with like the biological background. So I might try to incorporate more of that into his model as well, for those who need the refresher. Another thing I'll do is enhance readability by changing graph positions or graphs themselves. So kind of how like we did a few weeks ago in class where we had the graphs so they appeared side by side. I try to do that because a lot of his graphs are stacked on top of each other, and especially the ones where you're trying to compare, for example, these ones down here, it's kind of difficult to see any difference at all. It might be a little bit better to have them side by side. But then another thing I'd like to work on is verify this antibiotic resistant model, which I'll do by comparing to past literature. This part of the model is basically going through different treatments, I think, and what happens when people stop them, if I'm not mistaken. And as you can kind of see, perfect cooperation obviously is ideal. And then there's people that, I need to remember the acronyms, self-administered therapy versus direct observed preventive therapy. Self-administered therapy is probably going to be a bit less successful than whether or not people perfectly cooperate. Right now, the graphs look basically the same, which maybe that is right, but I'd like to verify that. And if it is right, maybe think of a different way to present this material, because right now, as it stands, it's just a little bit like, I don't know, like confusing on what it's trying to express, in my opinion. And then finally, if I have time, I'd like to maybe briefly discuss and compare to COVID-19 and maybe show the SRM model we kind of developed in class. That's just because if we're assuming like the audience that's, using this application are familiar with COVID, if it's being used within the next, within the current times, it might help give some context, especially to people who aren't as familiar with tuberculosis, since it's not really, I feel like it's not talked that much about in the United States, just because, we don't even take the vaccination for tuberculosis here. Other countries do. It just hasn't has much of an impact on us, I think, as a country, than it does for other countries. So for populations like that aren't familiar, that might help give it some context. And then with that, I would maybe briefly discuss the difference between a viral infection and a bacterial infection. So those are kind of the improvements and additions that I have. I still need to kind of do the work and implement them, but that's what I have. So, thank you.
Great, thank you very much. So I hope you'll be able to make some progress, and I think it's a good effort. It's as you say, it's a strong project, and improving it is well worthwhile. And I'm glad you're in touch with Nico on that. Anything else that people want to say before we? Okay, Colin and Delaney, how is your project coming along?
It's coming along. We have a little bit more of the application that we could show. It's not published yet, but we have sent in the app to NanoHub, and it's being processed at the moment. But I could share screen really quick.
Right, that's always an issue with NanoHub, that it takes time from the time. That's one reason I tried to encourage people to try to do everything a little early, is that it takes time for things to get put up on their site. And so that's
yeah, there was a class that we had to do this or NanoHub application for last semester, and I remember that being a problem. So we're going to make sure that's on track. But this is pretty similar to what we showed last week with the biological backgrounds regarding the HIV models. And all we've really done is we added on to a bit of the mathematical representation. I mentioned the initial modeling of viral infections and stuff like that with just how general network models work. Showed a basic S to I model parameters. This screenshot didn't load for some reason, but it shows the S to I model just to basically introduce people to how these network models are supposed to work. Reproduction numbers are explained briefly. And then I introduced the general papers additions to their own HIV model and the parameters and descriptions of those that they used. I looked at all of these, and I also looked at I made sure that the users understood the mathematical concepts and formulas that they were using for the differential equations, along with the initial condition and stuff like that. Basically just to simplify what the model we'll be using from the paper in our main model will look like. It just kind of made a simple diagram. I also discussed briefly the impact of changing the model parameters to introduce the users to sliders and basically altering the specifics of parameter values within the model and how it will affect them. You can change gamma and beta, which I explained briefly how these impact the overall infected cells over time. I then went into a little bit more, or we go into a little bit more complexity in terms of the overall model that the paper initially used, and I included more of the parameters, making some assumptions that certain parameters like death rate and birth rate were always the same. And this is just another way for the user to basically interact with the models that were used in the paper and that we'll be using throughout the rest of this. And beyond that, I have just a few basic questions that kind of like will allow the user to answer for themselves as they use sliders and stuff like that to examine the models. I also have briefly then discussed, Delaney had coded in the parameter sweeps, so these were mostly done by her. I'm not sure that she has connection right now though. But so we just discussed these parameter sweeps for each of the model parameters and discussed how they were basically affecting the final number of infected cells and what this could mean for the overall model. And I just have a few of those. We have a few more of those to put in. And then, as we mentioned last week, and we still have yet to do, we look to model HIV prevention methods and how those would slow down the spread and basically reduce the population risk of any further infection. And below is just the general code that we have been using. We'll obviously be cleaning it up for our final presentation and for further application aspects, but that's about it for now.
Some of those parameter sweeps are interesting. Could you just come back to one of them? And so the model is an oscillatory model. And so here you have the final number of infected cells versus the death rate of uninfected cells per day. So when you say final number in a situation like this, what does that mean?
Final number over the course of a certain number of days, which I believe was 100 or so. I suppose we could also change these parameter sweeps to be average number of infected cells, which I think might be a little bit of a better representation, considering that it goes, as you said, it's oscillatory, so it might not be relevant to the final number based on the day.
Right, because if you truncate it 100 days, then depending on where you are in the phase of your oscillation, you get a different result.
Mm.
And so that might be more meaningful.
Yeah, that is a good point.
Let's look at the next one. So Yeah, so here again, the final number of infected cells. I mean, it's possible that you really do have an oscillation in that result, but you'd want to know. I think you want to be careful because you don't want the final result to depend just on where you cut it off in the plot.
Mhm.
So I think you could look at the what happens to the maximum value or the average value at long times. Might be, as you say, might be better. So I don't know if that oscillation there is real or not. I mean, it's clearly real, but based on what you defined. But if it's meaningful or not.
Mhm.
So it may be that that's a smooth curve of increase, a smooth increasing curve, rather than an oscillatory one.
Yeah, we
But
can look into those. I agree.
something to look into. But it's. And then the next one was
The maximum T
no,
cell.
that's also on final number.
Mhm.
And so again, I don't know. I don't know if that's the thing that's happening there. Even if it is, it looks like that there's a non-trivial result where it goes down and then up again. And I don't know in your source paper what did the source paper do for analysis? How did they present their results?
I would need to look back at it. They did parameter sweeps. I think there was one based on final number, although I'm not sure we used the same time frame. And I think there were some based on averages, which we hadn't gotten to yet, like average per day or over a certain course of time.
And I guess I had one other question. You showed that nice time series of the T cell, infected T cell load, and so on early on. Are there parameter values where that oscillation disappears, or is there always an oscillation?
That was one of the questions I formed. I forget exactly which combination of parameters that there was minimal oscillations, but that was one of the investigations I wanted people to try out, basically. But yeah, I can't really recall what quantities were needed for which that situation to occur.
Well, that looks like you're losing your oscillations there. So it's taking it a while to catch up with your.
Yeah.
So one thing you might want to do is when you do this simulate, when you set up your sliders, you have an option to update continuously or only update when you release the slider.
Mm.
And you might want to set it so it updates on release, so that it doesn't get lagged like that. Although there are sometimes it's nice to actually have it update continuously. You have to think about it. So there you get a steady state, and that's okay. So you get that first initial peak of infection, and then you get a steady state. In this case, the amount of virus just goes up and stays up. What happens if you increase beta now slowly? Okay. Wait, you have to wait because it takes time for it to adjust.
Mm. Yeah.
Right? Because recalculating and redrawing every time you move a tiny amount, so there's a lag. So here the oscillations are still dying out, and you're reaching a steady state. And what happens if you increase the replication rate of the healthy T cell? So that doesn't do much. It looks like it mainly. I'm not sure what that's doing. It's interesting. I don't know. And if you go the other way on that, what happens? You bring it down. You've drawn the replication rate of healthy T cells up to the okay. Okay, so that okay, so that causes the oscillations to come back. Yeah. So what's a bit puzzling to me is, so T is the number of healthy T cells. Is that right?
Yes.
And I and V essentially track each other. Okay. Interesting. I think it's an interesting model, and I think there's a lot you could do with that. And there always are questions with a model like this about what controls the amplitude of the oscillations, what controls the period of the oscillations.
Mhm.
Again, whether the oscillations die out and reach a steady state or not. And so those are things that one can evaluate. Okay. Anything else about it you'd like to discuss at the moment before?
No, I think that's it for now.
Okay. Okay, thank you. Well, I guess we don't have Drew and Ryan here today. Thank you, everybody. So let's come back then to where we were. I don't know if we'll get through everything that was left over from last time, but we'll do our best. So I'll remind you that the past few weeks we've been talking about this idea of phenomenological rate laws. In particular, the idea of thinking about very simple questions about the way rate laws depend on their arguments, their variables or parameters, and to try to help people think about systems where you don't know exact results. And one way to do that is to ask the question, what happens when the parameter value is 0? Is the value automatically 0? For example, if I have no uninfected individuals, my rate of infection better be 0 because there's nobody to infect. If I have no virus, my rate of viral infection should be 0 because there's no virus to do the infecting. And so if the value is the rate of viral infection, and I'm asking it what it is as a function of the amount of virus and the number of uninfected individuals, it has to go to 0 for both arguments. And then you could ask the question, what's the slope at 0? Does that rate go up starting at 0 or not? In the case of the number of uninfected individuals for fixed amount of virus, you would expect that the rate of new infections was linear in the number of uninfected individuals because each person gets infected independently. But you could imagine situations in which nothing happens until you get some finite amount of something. In the case of many infections, your body is able to reject a small number of viruses when somebody coughs on you. But if the number of virus particles that you're exposed to is large enough, you become infected. So there's a nonlinear response. In that case, the slope might be 0 at 0. And then again, asking the question at very large values, what happens to the rate? Does it go to infinity? Does it go back to 0? And does it reach a steady state? And then you can build some simple functional forms that have that behavior. If the slope is non-zero at 0, the value is 0 at 0, the slope is 0 at infinity, and the value is finite, then you tend to get these what are called Michaelis forms that I've drawn here. And that's a typical functional guess of how the system is going to behave. You can make those things more complicated. I don't want to go into too much detail. We talked about it a lot before. But if we try to remember back to the distant past when we were talking about our viral infection model, one of the things that we might want to do is ask the question, if we have immune cells that are going to be imagined to be coming in and killing our infected cells, we'd like to know how fast the immune cells can kill our infected cells. And this is something that's quite important in your body, because in general in your body, once the cell has virus in it, the only way to get rid of the virus is for the cell to die. Cells in humans at least don't generally clear virus inside themselves. And so the cells can die for two reasons. They could die because the virus themselves is killing them. Actually, I guess there are more than two. They can die because the cell recognizes it's infected and it dies spontaneously. Or it can die because some component of the immune system, either the innate immune system like a natural killer cell, or the adaptive immune system, something like a CD8 plus T cell, comes in and kills the cell. If we think about target cells, infected cells being killed by natural killer cells or CD8 plus T cells, then we have to ask the question, if the cell's dying spontaneously, each cell can do it independently. So the rate of cell death is going to depend on the amount of virus inside the cell and the state of the cell, but it won't depend on how many infected cells are infected at any given time. On the other hand, if we have a finite supply of immune cells that have to go around and kill the target cells, then we have to think about a number of relationships. If the number of infected cells is very few, and you have very few immune cells, then once an immune cell is finished killing a target cell, it's going to take it a long time till it finds the next target cell. And so basically the time, the rate at which the immune cells can kill the target cells will be controlled by the distance between the target cells. And if I increase the number of immune cells, the rate of killing should go up more or less linearly with the number of immune cells. If I increase the number of target cells, the distance between the cells goes down. So the time to get from one to the next goes down. And so the rate of killing also goes up. On the other hand, if I have a lot, suppose every cell is infected. If every cell is infected, the immune cells don't spend any time finding the next target, but it takes them some amount of time to kill. And that amount of time is independent of the number of target cells. And so you have a saturation where the rate of killing per immune cell can't be faster than 1 over the time it takes to kill. And so you get a variety of what saturation laws. And exactly how those things combine is not, I think, well understood. That's something that we could definitely, next semester, that would actually be a very good simulation to do, would be to do a simulation of how the rate of immune cell killing depends on the number of immune cells and the number of target cells. In the case where you have non-zero, a zero value at 0 and 0 slope at 0 and saturation, you have what's called a sigmoid. And there are many different shapes of sigmoid that you can draw. There's a simple functional form called the Hill equation, which basically goes parameter to the n divided by k to the n plus parameter to the n. And in that case, if n is 1, you get the case we did before, where the slope is not 0 at 0. If n is between 2 and infinity, you get something that is called a sigmoid. The slope is 0 at 0, slope is 0 at infinity. The value is always a half at a half. And the steepness of the step goes up as I increase that exponent, n. And so if I make n just above 1, I get something that's very smooth. If I make n very, very large, eventually I'll get a perfect step function where my value is 0, between 0 and a half, and then jumps up to 1 for values bigger than a half. And typically when you see whole functions, it's a statement about not knowing the details of how a process works. But in general, that kind of a Hill approximation is used a lot to hide our ignorance. Okay. We also did a couple of weeks ago a little bit of an exercise in translating back and forth between arrow diagrams, ODEs, and Animony, and I'd like to review that. And you can tell me how much of this you want. People a couple of weeks ago asked to come back to this and do it in a little bit more detail. But if people feel comfortable with it, we don't have to spend a lot of time on it. So you can tell me if you'd like to go over this again or not before I launch into it. Would people like to see? Would people like to go back over this issue of how do you go from arrow diagram to math to Antibody, or do people feel comfortable with that? If people raise your hands and say you can raise your hand if you'd like to see me do it, you can say yes. And if I don't see anything, then I'll skip through it pretty quickly. Okay, so it sounds like now that people are doing the exercises, maybe they don't need to do this because you've been doing it enough. So I'll skip over it pretty fast then. So let's just quickly review how to turn arrow diagrams into ODs and Animony. The first thing that we have to remember is that arrow diagrams basically represent changes, and there are multiple kinds of changes that can be represented. The arrow diagram originally came out of chemical reaction modeling. And so you'd have a chemical reaction like two molecules of ADP can combine to form a molecule of ATP and a model of AMP. Adenosine diphosphate goes to adenosine. Two molecules of adenosine diphosphate give you one molecule of adenosine triphosphate and one molecule of adenosine monophosphate. Essentially, what's happened is one of the phosphates has moved from one of them to the other. Notice that in our world of epidemiology and in-host viral kinetics, we don't usually have bidirectional arrows. If you become infected, you typically then move to another state. But if we had a situation where you go from susceptible to infected and then back to susceptible, we could draw that with two separate arrows, or we could draw it with one bidirectional arrow. In chemistry, it's usual to have bidirectional arrows, and that means that you actually can have two rates associated with each arrow, one for the forward arrow and one for the backward arrow. And there are a variety of notations that are used for that. Multiple headed arrows, multiple tailed arrows. Sometimes they try to indicate the stoichiometry, so this would be trying to indicate two A's go to B, B makes three C's, and so on. That's pretty cumbersome to have multi-headed arrows, but people use it. We talked about some of the basic notation and its inconsistencies, in particular the idea of mass transfer, which is the basic idea that's in antimony, those arrows that we use all the time in antimony. S1 becomes S2, so that means that S1 is used up and S2 is created. And then regulatory arrows, which could be excitatory, A, activating, or repressing or inhibitory, R, with a blunt end. And the key difference is that in reaction arrow, S1 is used up to make S2, but a regulatory arrow, A, is not used up in the reaction. S1 goes to S2. If A were actually incorporated into this, we would have a two-headed arrow where A comes together with S1 to make S2. So that's the difference. And so when we're going to do this, and this was in the homework, which we did a little bit at the end of class last week, we have to understand how to interpret this kind of diagram. We might have a situation where S1 becomes S2, and that's promoted by A. That would mean the rate of production of S2 is increasing as the amount of A is increasing. And this should actually be a dot really on top of the S2. It should be a time derivative. So there's a typo in this slide. Sometimes people will write A promotes S2 without indicating where the S2 is coming from, or R inhibits S2 without indicating where the S2 is coming from. And so there's a lot of ambiguity in these rate diagrams. And so you have to learn a little bit how to interpret them to understand what they mean. From the point of view of antimony, we're always writing things as reactions. And so if we see that A is promoting S2, we interpret that as nothing is going to S2 with a rate that depends on A. And that would be nothing goes to S2 with a rate that depends on A. And so that now this is something on the right is something that we can understand in antimony, because this is essentially how we write everything in antimony. We would have nothing arrow S2 semicolon V1 of A. Another thing that we have to worry about in chemical reactions, which may or may not be present in our in-host models, is that no chemical ever has an infinite lifetime. And so our molecule S2 always implicitly decays to nothing again. And that decay is usually what's called first order kinetics. The rate at which you lose S2 is proportional to S2. It makes sense at the zero end. We'll ask the same questions as before. If you have no S2, what's the rate at which you lose S2? It has to be zero. So the value, the rate law for the decay of S2 has to be zero when you have no S2. And so that means that the value is zero at zero. Each decay of the molecule S2 is independent of every other one. And so you expect that the total decay rate would be proportional to the number of S2, which means the slope of the rate at zero is non-zero. And it means that the value at infinity is infinite and the slope is infinite. That sounds fancy, but that's equivalent to saying the decay rate is a constant times S2. And so if I see this diagram, A promotes S2, I have to first write it as nothing goes to S2, and then I have to intrinsically add S2 goes to nothing again. And that was where we were ending last time when we were trying to build those examples in the homework problem. So if we think about this in the example of our in-host model, we have susceptible cells becoming infected at a rate beta times V times T, and that's something that we can interpret. That means that on the left we're losing T, we're losing susceptible cells. So this rate law tells us that dt, capital T by d little t, by time, is equal to minus beta Vt. There's a balance equation. If I'm losing t's, I'm gaining I1s. And so di1 dt is equal to plus beta Vt. I then go to the next line. I1 is turning into I2 at a rate ki1. That's the first order kinetics I was talking about. So that would mean I have an additional term for my I1 equation. di1 dt is equal to plus beta Vt minus ki1. And what about I2? di2 dt is equal to plus ki1 minus di2, and so on. Notice that in the case of the virus, I don't have the virus coming from one of these. I'm not converting T, I, 1, I2, or D into virus. These cells are producing virus. And so I have nothing goes to virus, and virus decays. So dV dt would be plus PI2 minus C times V. And so again, each arrow, if the arrow is anchored on two species, that one arrow generates two terms, one in each of the differential equations, one for I1 and one for I2. Right. I reminded you before, and I'll say it again because you'll run into it in the papers you look at, that while it's technically you should write always the rate law, the full rate law, on top of an arrow, the way I did, very often people will assume that the rate on top of the arrow is multiplied by the concentration of the species on the source of the arrow. And so T goes to I1 at a rate beta Vt will be written T goes to I1 at a rate beta V. And very often they won't tell you which way they did it. If you look at the ODs, you can figure it out, but very often they won't tell you which one they assumed. One way to check is that if you see something disappearing entirely, V goes to nothing, and it's got just a constant sitting on it, then they have to be using that convention, because you can't have virus disappearing if you don't have any. And so when you see a decay term, it always has to have at least some factor of the variable multiplying it so that the rate goes to 0 at 0. There's an additional complication, though. What if I see something like this? Nothing goes to V at a rate P times I2. What do I have to do? For this arrow, I see nothing goes, V goes to nothing at a rate C, and I interpret that as V goes to nothing at a rate C times V. If I see this arrow, I see nothing, T goes to I1 at a rate beta V. I interpret this as T goes to I1 at a rate beta V times T. If I see nothing goes to V at a rate P times I2, I'd say, well, I need to multiply it by something. But I look around and I'd say, what can I multiply it by? There is only one thing I have available to me to multiply by V, but that's not right. And so if the arrow has nothing on its left, I don't convert it. So arrows that have something on the left get changed. Arrows that don't have something on the left don't get changed. Another reason why this notation is confusing, because to make the math out of it, you have to know all of these rules. Okay. As I mentioned before, you can write ODEs directly in Animony with a prime. dt by dt equals minus beta vt. T prime equals minus beta times v times t. This means that this Animony string will give you one term in one ODE. If I use arrows, each arrow will generate, if it's between two species, will generate two terms. And so I have to decide whether I want to write everything twice or not. If I use the ODE notation, I have to write my terms twice. And so we have some examples here, which I think we worked through some a couple of weeks ago. So again, we can go through the steps. How many equations does capital T appear in? Capital T is on the left-hand side of an arrow, not on the right-hand side of any arrow, so it occurs only once. I1 is on the left-hand side of an arrow in the top, and on the right-hand side of an arrow, on the right-hand side of an arrow on the top, and the left-hand side of an arrow in the middle. So there are two terms in my I1 equation, and so forth, going through. My V is between a left-hand arrow and a right-hand arrow. And again, that means it'll have two terms for the equation. And so I can write directly the Animony strings for the ODEs, or I can use the arrow notation. Nothing goes to a variable is equivalent to writing variable prime, have the same effect. If I write t goes to I1, rate beta times v times t, that gives me both terms that are associated with that. So we don't have to go through that in more detail, because I think you've done it before. But we can then walk through this process, and we see t goes to I1, rate beta vt. We write directly t goes to I1, semicolon beta times v times t. I1 goes to I2. I1 goes to I2 at a rate k times I1. So everything gets translated directly if we have the arrows. If we start with the ODEs and we want to turn them into arrows, it's a little bit more complicated. We can always write them out inefficiently by writing nothing goes to x, semicolon rate. And that we just write that for each ODE. Instead, though, if we see a set of equations that look like the ones on the right, what we'll notice is that we have what are called balance equations. We have d capital T by d time, di1 by d time. We see minus beta vt, beta vt. When we see a pair like that, we can always write t goes to I at a rate beta vt. And so if we want to convert ODEs into arrows, typically what we have to do is look for paired terms like that. And in particular, you want the arguments of those terms to depend only on the thing that's on the left-hand side of the arrow. And so here we see beta vt, ki1, ki1, di2, di2. That tells us that we should write this as three arrow diagrams. T goes to I1, I1 goes to I2, I2 goes to D. Notice that for the amount of virus, the concentration of virus, dV by dt, we have PI2 minus CV. There are no balance terms with anything else. And so for that, we have to write that as two independent arrow diagrams. Nothing goes to IV at a rate PI2, and V goes to nothing at a rate CV. We don't gain anything by the arrows. In fact, we need two arrow diagrams to represent one ODE. So sometimes we gain by going to the OD form in terms of compactness, other times not. It's important to say, though, that when you have the ODEs, you can't always get a unique arrow diagram, because when you have the arrow diagrams, you can always get a unique set of ODEs. And so we could play this game again, and this is simply showing that there is no unique way to write the arrows from the ODEs. These arrow diagrams both give the same set of ordinary differential equations, but I've grouped things differently. The first one, I've basically used that arrow notation to write the ODEs directly. Nothing goes to T, nothing goes to I1, nothing goes to I2, nothing goes to D, nothing goes to V. The second one, I've written it in this transformation notation. T goes to I1, I1 goes to I2, I2 goes to D, nothing goes to V, V goes to nothing. In the case of the first three, I've grouped things in a way that makes sense because I know T really does become I1, I1 does become I2, I2 does become D. And so that grouping makes a lot of logical sense. Notice that I've simplified the right-hand side for the rate laws. For the virus one, I've actually made things look a little bit more complicated because I've broken that one virus equation into two. And so these are systematically things that we can do. The other thing that can happen in Animony, if we're writing Animony, is we could have multiple arrow diagrams involving the same chemical species. You could have oxygen produced by one chemical reaction and oxygen produced by another. What's the rate of oxygen production? The sum of the rates of the two independently. And so if we want to convert Animony into ODEs, we have to convert each term separately and then add them up. So if I have, for example, J0, nothing goes to A, at rate K1. J1, A goes to B at a rate K2 times A. This gives me, first, dA by dt is K1. It's a source, constant source. A goes to B at a rate K2 times A gives me two equations, dA by dt minus K2A, dB by dt is plus K2A. If I want to know what my total rate law for A is, I have to add the contribution from the first one and the second one. So I get dA by dt is equal to K1 from the first equation minus K2 from the second, A times A from the second one. Here, that's not so complicated, but I could imagine having many equations which involve A, and then I might have a lot of terms to keep track of. So I have to be a little bit careful to make sure that I keep up with all of that. What I've drawn here is a cascade reaction. Nothing goes to A. I provide a source of A. A goes to B, B goes to C, C goes to D, D goes to E, E goes to F, F decays. That's a classic cascade chemical reaction. That kind of reaction happens a lot in biology where you get stacks. And so you see here, the A reaction, the A ODE depends on J0 and J1. The B ODE depends on J1 and J2. The C ODE depends on J2 and J3 and so on. And I wind up getting two terms in each equation A is produced at a constant rate, decays. B is produced at a rate proportional to A and decays, and so on. You see the balance terms, A, B, B, C, C, D, D, E, E. The only two unbalanced terms are K1 and K7F. Okay. If we want to convert antimony back to arrow diagrams, in general, we're starting with arrow diagrams, so that's okay. But there are a couple of things that are a little bit more complicated. If we see the same chemical species show up multiple times, in principle, that means that that species has to be at the beginning or end of multiple arrows. Nothing goes to A goes to B. Therefore, there's an arrow into A and an arrow out of A. If we go from here, what would the next one be? What would the next step of this reaction be? Somebody? Can you help me out on that one? Allie, does this make sense at all?
Yeah, could you repeat the question really quick? I was just writing stuff down.
Okay, so let's just do this example. We started out with J0, nothing goes to A at rate K1. J1, A goes to B at a rate K2 times A. And now that gives us two arrow diagrams, which get concatenated. Nothing goes to A at a rate K1. A goes to B at a rate K2 times A. What comes out of B? What's the next arrow? Maybe the question is so simple it seems trickier than it is.
Is it K3B?
B goes to C at a rate K3 times B, yes.
Okay.
And then for C, what would the next one be?
Goes to D at K4 times C.
Okay, 4 times C. So what you're going to get is a single line with arrow to A to B, B to C, C to D, and so on. One long line like that. And if you look in a chemistry or biology textbooks, you'll see chains of reactions that look like this. Now, typically, there'll be things coming in and going out. It won't just be a single linear chain. It might be A plus F goes to B, C plus D goes to D, C splits into D and X, those kind of things. But this kind of chain is the classic thing that you see in biology. So something that I wanted to talk about a little bit, which we really didn't get into in this class very much, but is something that's important, and we talked about it a little bit in the context of epidemiology, which is how do you deal with delays? And everything we've written in Animony has the form of nothing goes to A at a rate K1 means that dA by dt is equal to K1. A goes to B at a rate K2 times A, dA by dt equals minus K2 times A. Those all have one particular feature, which is that the rate depends only on the amount of A and B now. But in many situations, your HIV one was a good one, and the tuberculosis is a good one. What's happening now doesn't depend on the value now. It depends on the value at some time in the past. So trying to think of a good example of this. I mean, there are many of them, but suppose that a cell becomes infected with a virus. In our models, we've assumed that the cell immediately starts releasing virus, that the rate at which the virus is produced is proportional to the number of infected cells, or at least the number of virus-releasing cells. In reality, it takes some finite amount of time before the cells start releasing virus, and during that period, they produce no virus at all. So the amount of virus being produced now depends on my being infected 2 hours before or 4 hours before. And it winds up that you cannot represent perfectly a delay, a perfect delay, with this kind of ODE model. And so what you'd like to say is, suppose we look at the top here, the change of I by time is equal to X, not now, but at a time in the past, at a distance tau in the past. And we haven't gone much into the mathematics of delays. We haven't really done much mathematical analysis in this class. But one thing that you find is that the dimensionality, the number of variables in your problem, in the case of our arrow diagrams, it's very simple. The number of variables is A, B, C, D, E, F, 6. If I'm only talking about the value now. But if I depend not only on the value now, but at the value in the past, then I depend on the continuous infinity of variables, of values. And so I've switched actually from an ordinary differential equation situation to what's called a partial differential equation system. And the complexity of the problem has gone up. And it winds up that there's no universal way of numerically solving delay equations. And so while the ODEs that we work with so far in this class are relatively easy to solve, you may have occasionally run into this C-vote error where there's a convergence error in your numerics. But in general, solving ordinary differential equations numerically is straightforward. Solving delay equations numerically is not straightforward. And it happens if you use MATLAB, which generally I'm not enthusiastic about. If you use MATLAB, it has some good solvers for specific cases of delay equations. And Python has some custom delay equation solvers as well. But Animony doesn't let you write delay equations. And that can be a problem in the past when people have wanted to replicate papers. For example, Alan Perlson writes a lot of very simple reaction models of network models, infection models, but he typically will use delays in his models to represent real biological delays. And then somebody will come and say, I want to reproduce one of Alan's papers. And we say, well, too bad, we can't really do it because you can't write delay equations in Animony. And the reason that I have this cascade reaction up here is because one of the ways that you can do delays is what's called a bucket brigade. And this is a classic numerical way of doing it. You create a stack and you put the value now at the top of the stack. And then a few seconds later, you put the value then and add it to the stack. And then a few seconds later, you put the value again and again and again. So you keep adding to the top. And once you've gotten to the delay time you want, you start taking things off of the bottom. And that kind of delay where you pass information from now to next time to next time to next time to next time is called the bucket brigade, and it's used all the time computationally. It's not very elegant, but it's used all the time computationally. And if you do it actually by copying the value, then it's exact. Animony doesn't let you do that, but if you think about nothing goes to A goes to B, you think about A going to B as a transformation with a rate, K2 times A. You can think about essentially the picture we've got here, J0 through J6, as 6 lengths of garden hose, where the first length is not from the spigot to the first part of the hose. The second part is from the first part of the hose to the second part, and so on. And the rates are the flow rate. And if we think about it this way, this stack of reactions effectively is passing material from A to B to C to D to E to F. What's a little more complicated about it, though, is that because we're not actually doing a discrete passing, even at very short times, there will be some, as soon as A is non-zero, F will not be zero either. It's going to be very small, but it's not zero. Whereas if I really had a bucket brigade, F would stay zero until I'd passed A to B to C to D to E to F. And so it's not a perfect approximation. If I ask how long is the delay, I could ask the question, what are the rates? K1, each one of these rate constants, K1, K2, K3, the bigger that rate constant is, the faster material gets passed down my chain. And so that means that the delay of each one of these is roughly, very roughly, 1 over the rate constant. So the time it takes A to turn into C is approximately 1 over K2. The time it takes B to turn into D is approximately 1 over K3 plus 1 over K4. And so the delay for this whole stack of reactions, A to B to C to D to E to F, is approximately 1 over K2 plus 1 over K3 plus 1 over K4. And the way we can see this in a simulation would be if we take K1 not as a rate, but imagine K1 is the signal that we're applying. And the signal starts out at 0 and then goes up, stays up, and then comes down. So here is a simulation, and I don't want to take the time to do this exercise. It's something one can do at home. So what I did here, and I can give you the example code in a bit. Sorry, I don't have Giuliano here to put the code up for you. Is suppose that we imagine that K1 is now not representing a rate, but it's actually representing some input signal. And so we'll say that K1 is 0 up till 10. It then increases rapidly to reach a value of 1 at time 20. It stays constant from 20 to 60, and then it decreases linearly again till 0 at 7. So that's our input signal, K1. And our question is, what do B, C, D, E, and F look like when we've done that? We can start out with all of our rate laws, rate constants being 1, and we'll now plot F on top of this. And if I do that, what I get is something that looks like this. where F, the output, you notice that it's not square. It's not a sharp, it doesn't delay by 5 or 10 and then go up linearly and then stay constant and then come down. But it's pretty close to that. Initially, it starts going up a little bit too soon. It rounds off instead of having a sharp corner at the top. But then it stays constant along the period of time that it should. Then it stays up for a while, rounds off again, comes down, and then it goes to 0 again. And so effectively, what we've done here is we've created something that looks pretty close to a delay by creating this stack of chemical reactions. That's a very inelegant way of doing this, but it's the best I've been able to come up with when people want to do delays. And if somebody has ideas about better ways to do that, it's something to think about.
Can I ask a question?
Yes, please.
How come for like the arrows going from D to E and E to F and F to tau, the constant's K2, but then I think in the code it's like K5, K6, K7.
Oh, thank you. Good. You caught a typo.
So should they be K5, K6, K7 then, or?
Yes, absolutely. That's a cut and paste error.
Okay.
So draw. It's something. It's PowerPoint or Microsoft Word, which is putting the rates over the arrows is a pain using the equation editor. And so I do it once and then I copy and paste it to make the chain. And then I forgot to change the subscript. So thank you very much for doing that. In fact, in the initial example that I gave, I set all of them equal to 1. I set K2, K3, K4, K5, K6, K7 to equal 1. To get that value. If you look at the Animony code that I have on the right, the code is actually doing something a little bit more complicated because I have K2 equal to 1, K3 equals K2 times a number, a ratio, K4 equals K3 times that ratio, and so on. So they're actually geometric regression. And that's something that one can play with. And to get the delay to work properly, you may not want all those rates to be the same. But thank you for catching that, and I will fix that. Let me make a note, actually, for myself. So that I get that fixed. Thank you, that's great. Appreciate it. So let's actually do the one I've skipped us through a bunch of exercises, but let's actually just do one. So now let's take an example. This is a within host model of malaria, but it looks very similar to all the other models that we have. And I'd like people to take this rate diagram that we've got here, and I've asked you to write an antimony string, but maybe before you write the antimony string, it would be good to write the ODEs. So let's do this as a little exercise. If there are any ambiguities about what's going on in this diagram, let me know. But I'd like people to take a few minutes, just a few minutes, to try to write first the ODEs for this arrow diagram, and then the corresponding Animony string. Is that okay as an exercise? I think you've done this when you tried to interpret other papers, but as a reminder, why don't we try that? Okay. Delaney, did you have a comment or question on that? So everybody try to write the rate laws and then the Animony for this.
I sort of skipped right to the writing it as a antimony string.
Yeah, that's fine. Anybody else? How did it work out for people?
So to represent like the regulatory arrow, do we use the like the equation that's like from last class? It was like in the example we did, it was like V over 1 plus A over K. Is it like similar to that?
So perhaps this is a deceptive exercise because it's actually so easy. All the rates are written on the arrows, so you don't have to guess. All of the rates are written on top of the arrows here. One question could be: does the rate laws require that you multiply by the source? And remember how to check that. How do you find out if I have to do anything to rewrite the rate laws? What was my advice to look for? So remember, you look for decays. So here m is going to nothing, and the rate is written d times m. And so that means usually that the rates are as written. And so how many regulatory arrows are there in this diagram, Delaney? Sorry, you're muted if you're trying to say something. Ali, how's it going for you?
I guess I went about the long way, so I like did it the differential equations. Like I put in two equations first, and so now I'm like putting them into the Animony string right now.
Remember, the point of a regulatory arrow is that it doesn't show up as an arrow. A regulatory arrow, the only regulatory arrow in this diagram is M promotes U going to P. That's basically my infection term. Uninfected is going to infected at a rate depending on the concentration of malaria. This is our usual SIR model, as always. The fact that it says it's about malaria is really not very relevant. And the rate here is beta times U times M. So this arrow here, this regulatory arrow, is simply saying that beta times U times M depends on M. And the fact that it's got a lollipop at the end means that it increases as M increases. Everything else is our usual SIR model. I guess the one thing that maybe isn't so typical in the SIR model is there's a decay term on U and a decay term on M. Okay, is that making more sense now, Allie? And Delaney?
Yeah, I think so.
So this is what you get, at least if I did it directly. Again, each arrow in this diagram becomes one line of my antimony. I have nothing goes to U at a rate lambda. Well, I can't write lambda, so I'll write L. So nothing goes to U at a rate L. U decays at a rate mu times U. U goes to nothing at a rate M times U. U goes to P at a rate beta UM. U goes to P at a rate B times U times M. P goes to M at a rate R alpha P. P goes to M at a rate R times A times P. M goes to nothing at a rate D times M. M goes to nothing at a rate D times M. So this translates very directly. If we wanted to write the ODEs, we could do that for U. I'll have three terms. I'm creating U, I'm eliminating U through this arrow, and I'm eliminating U through this arrow. So I'll have one positive and two negative terms. Lambda minus beta UM minus mu U. P, I have one input arrow and one output arrow, so I have two terms. Plus beta UM minus R alpha P. M is big, has two arrows, one coming in, one going out. dm by dt R alpha P minus dm. So in this case, I have 1, 2, 3, 4, 5 arrows. 1, 2, 3, 4, 5 arrows. Transformation arrows. The regulatory arrows don't generate lines. So I have 5 arrows, so 5 lines of antimony. I have 3 species, 3 ODEs. I have how many rates? 1, 2, 3, 4, 5 rates. That generates 1, 2, 3, 4, 5 rates here, but some of those occur twice because if a rate has 2 species, one on either end of the arrow, it shows up twice. Beta UM, beta UM, RAP, RAP. So I have 5 arrows, but 7 terms in my ODEs. And so converting back and forth among these 3 notations is something that we've had little practice with, and I hope people will continue to deal with. Again, if you're going to work with these more in the future, you'll get a lot of practice doing this. Okay. So now we can come back to where we were. It's been a while, so I want to remind you that we had actually almost exactly this model for our viral infection model, and this is now reaching back several weeks. We kept talking about, I'm sorry, Delaney, if you're having connection problems. I know how frustrating it can be when that's like that. Coming back several weeks, and I'll just remind you where we were when we stopped. We were modeling influenza, and we had a basic model that looked rather like what we just did, with the idea that there was also a latent period. And that latent period was actually the motivation for talking about delays, because there should really be a delay. And we're going to approximate things without a true delay. So we had our uninfected cells T. They were infected by virus. They produced a eclipse or latent phase I1. Those I1s became virus releasing cells I2, created virus, the virus decayed, and the I2 cells could die. And in this case, we had them dying at a constant rate. And so that gave us this stack of equations, which we've seen many times, and which we've walked through just now. And we had a Animony code from a long time ago which did this. And when we ran that code, what we saw was, in fact, the first couple of phases of the viral load, viremia, in the patient. We saw a short delay at the beginning, a rapid exponential growth of viral concentration, a period when the virus concentration reaches a maximum, and then a slow decrease of the amount of virus in the system. And I guess it would be nice if people can fire up tellurium, since it's our last class. Maybe it would be good to do that. Why don't people fire up tellurium? If you need help finding this model that we had from a few weeks ago, let me know. But it should be in the example file from lecture. This is 15, 14, 13. I think lecture 12. We may have to look around for that. So while you're getting tellurium going, I will go and find where that model is hiding, okay? Okay, was everybody able to get that up and running? Okay. So finding your way around this may be problematic because it's pretty long. The place we are is in this cell that's called infected cell clearance due to viral infection and innate immune response. So maybe take a minute to find your way down there. And you should see this code here, which is exactly the code we have in the slide deck. Now, the things that I have programmed to plot in this demo may or may not be exactly what I have on the screen in the slides, because there's some extra plots that are put into the demo. Is everybody able to find that all right? If you need help finding it, let me know. There was a question earlier about how do the slides relate to the Jupyter notebooks, and that's a relevant question here, because in fact what I tried to do here with the Jupyter notebook was make it self-contained, and so there's going to be a certain amount of overlap between the content of your notebook and the slides, but they're not going to be identical. Okay, great. So let's run that. And if you run it, you're going to see some extra plots. I've disabled some of them here so I can display it. The key thing that we'll see, what I did originally was that I plotted this this plot both for the parameter values that are relevant to influenza, and then also estimates for COVID. And here I've turned off the COVID-related ones. You'll see an extra pair of plots to compare the two. The top graph is a plot of the cell populations on a linear scale. And what I see is blue is the number of uninfected cells. All the cells are infected by the end of 2 days, which is about right for influenza. Actually, of course, not all the cells in your lung get infected or you die, but in the model they do. Then we have our peak of latent cells, the orange, the I1 cells. Those I1 cells go on to become I2 or virus-producing cells. And those virus-producing cells, the green ones, eventually die, and you see red, which is the gradually increasing amount of cell death. In reality, if this is how your body cleared virus, you die, because all the cells in your lung would die. So the model isn't that great. And here's the viral load, and notice here I put it on a log scale to correspond to the experimental data set. And what I see again is that there's a short delay. The delay here seems to be quite short, shorter probably than in reality. This rapid exponential growth, the saturation, and then this slow decline that you see here. And here I have what should be the same plot showing the different regions and showing that it agrees pretty well with the experiment. And to go further, we're going to have to think about the adaptive immune system. And the model we're going to build of the adaptive immune system is not going to be the greatest, but it'll give you some ideas. And boy, trying to cover this in an hour may be a bit of a sprint. It'll give you a little bit of idea about how you might want to think about building more complicated models. Because pretty much everything people have shown in their in-host models, in the papers they've replicated and so on, all of that was based on classic SIR type models, SIRD models. And here we're going to try to think a little bit about maybe the biology and how to represent it. And I should say this model we're going to build here isn't the greatest. I pulled it out of the air, so to speak, on my own, not looking at what other people had done. Retrospectively, I should have looked at what other people did because they knew more than I did. But it gives you an idea about how you can think about a problem. So we have to, in order to go further, we actually have to think about the adaptive immune response. And the adaptive immune response is not the most enjoyable thing to model because it's pretty complicated. We have to ask first what the biology is. And so what happens in the adaptive immune response is that the cells that are infected in the lung die. The pieces of the cells that died, which have virus in them, are eaten by macrophages. Those macrophages and other related cells migrate out of the lung into the lymph nodes, which is why you get swollen lymph nodes when you get an infection. In the lymph nodes, those become, those dendritic cells become antigen-presenting cells. They look around for T cells, inactivated T cells in the quiescent T cells in the lymph node that have antibodies on their surface. Well, not exactly antibodies. They have antibody-like receptors on their surface that recognize the virus. And when the cells in the lymph node see the virus presented by the antigen-presenting cells, and they recognize it, they then begin to proliferate. And once they proliferate, they then migrate through the blood primarily back into the tissue and become CD8 plus T cells. And those CD8 plus T cells migrate through the tissue. When they encounter an infected cell, they kill it. And so the adaptive immune response has these multiple components. You have cells that start out in the lung. They send a signal to the lymph node. The lymph node has cells that proliferate, and that proliferation takes time because there's no way for your cells to reproduce more than about once every 10 to 12 hours. It's the fastest they can reproduce. Once they've reproduced, it takes a little bit of time for them to come back through the lymph and the blood, but that's not a huge delay. They have to then get out of the blood into the lung, which is a process that's non-trivial, although it doesn't have a huge delay. Once they're in the lung, they have to find the infected cells and they have to kill them. And so conceptually, what we have to do now is think about the signal getting from the lung to the lymph node, the cells in the lymph node proliferating, those cells coming from the lymph node back to the lung and then killing the target. It's a lot easier to do that actually in the spatial model than it is in an OD model. But that's what we're going to have to do. And the reason that we see this long delay of 7 days followed by rapid clearance is that that's the amount of time it takes for those cells in the lymph nodes to reproduce enough to come back to the lung to start clearing things up. And so we're going to do this in the form of a couple of signals. There are both cellular and chemical signals going on. And this model's probably the biggest defect of this model is the way it combines the cellular and chemical signals for the lymph node. But let's talk about that a little bit. When you get the flu and you begin to feel sick, the headache, the fever, the weakness are all not a result of the virus directly. They're a result of immune signaling molecules called cytokines. And those cytokines are produced by the infected cells in the lung and also by cells that sense and amplify that signal, although we're not going to include that here. In particular, macrophages, neutrophils will also amplify that signal. The particular species of cytokines are not that important for the model. In practice, interleukin-2 and interleukin-6 are probably the things that are making you feel crappy. They're sort of the master I'm infected signals that start off all of the complex processes of the immune system. In any case, we need to have some kind of cytokine signal that is produced by the infected cells. And we're going to assume that the infected cells, both the latent cells and the virus-releasing cells, produce this signal, this cytokine. And so we're going to now create a new species, C, which is cytokine. We're going to only have one of them. In reality, there are a lot of them. And we're going to assume that all of our infected cells produce cytokine at some constant rate, just the way the infected cells produce virus. And one defect we're going to find out of the model is that the virus and the cytokine are going to track each other too closely. As always, with any model of this kind, chemicals don't last forever, and so that we'll have to assume that the cytokine disappears. So the cytokine is going to be produced at a rate PC proportional to the number of infected cells of both kinds that we have. It's going to disappear at a constant rate. And the things that we have to assume, we have to know are how fast we produce the cytokine. That doesn't matter because it'll scale out later. So we'll just set that rate of production to 1. But the lifetime of the cytokine does matter. And it typically will last about 10 or 12 hours. They're fairly long-lived molecules. In reality, it may be a little shorter. So a lifetime of 12 hours is a half a day. That means our breakdown time is on the order of 2 per day. So we've added 2 parameters, PC and C, 1 per day and 2 per day. Okay, and so why don't we go to our next box where we've added that, and why don't we run that together? That shouldn't be too much. Does that work? The first plot, which is of we haven't done anything with the cytokine. So all we've done is add an extra readout. We haven't changed the number of cells of any kind because our immune system isn't doing anything at this point. Okay. Is anybody having problems getting that to work? And when I made a comment that it wasn't a very sensible choice that I made here. Here I've plotted the viral load in blue and the cytokine level in orange. And what I see is that they're essentially proportional to each other. And if that's the case, there isn't really any advantage in using the cytokine. I could just have multiplied the amount of virus by a constant and simplified my model. So you get that. So that is, as a base model, just saying that there is an immune signal. We haven't done anything with it. And so now we have to think about the more important thing, which is that we have to get a signal, and the naming of this signal is not very pretty in this model. We have to get this signal from the infected tissue, from the lung, to the lymph node, so that the cells in the lymph node can proliferate, so the immune cells in the lymph node can proliferate. In reality, this signal is both the chemical signal of cytokine and the migration of what are called antigen-presenting cells, APCs, to the lymph node. The migration of antigen-presenting cells to the lymph node is a little slower than the chemical transmission. And so what we're now going to do is create a species which is going to be called CL, which represents the signal combining the antigen presenting cells and the cytokine level in the lymph node. And we're going to assume that it takes time for the antigen presenting cells to get to the lymph node. They actually get there a little faster than we're going to assume, but 2 days is not an unreasonable assumption. They actually physically have to crawl from the lung tissue to the lymph nodes. There are lymph nodes all over your body, so they don't have to crawl very far, but cells are small, so it takes them time. They're actually actively moved by the liquid as well, so they don't take quite as long as you'd expect. Once they're there in the lymph node, they don't last forever, and so they are going to disappear with some constant rate. And we're going to assume that they last about 2 days in the lymph node. And so we're now going to write a new species, which is the concentration of antigen-presenting cells in the lymph node, and it's going to be proportional to the cytokine concentration in the lung minus the decay rate. And we're going to assume that both of these rates are about 1/2 per day. And so why don't you actually try adding that by hand instead of just, well, I guess we can just go ahead. It's up to you. If you like, this is designed so that you can add this into these examples by hand. And then if you have trouble and you can't get it to work on your end, the idea was to jump ahead and have it in the notebook. Since we don't have a lot of time, maybe it's better just to follow along and you can do this on your own later. So here we've created these, we've created the antigen presenting cells in the lymph node, CL, at a rate of 1/2. And we're going to run it. We have our viral load, and we have our cytokine, our antigen presenting cells / cytokine in the lymph node. And you'll notice here that there is a delay, that this orange curve is shifted to the right with respect to the blue curve. In reality, it should be shifted further to the right because the delay is longer than here. The delay is, let's see, that's 1 day. So the delay is about here, about 1/3 of a day. In reality, it should be a little longer than that. We could try playing around with this to see whether we could make that delay longer. Why don't we do that? Let's slow down the movement here. Here we'd said that it takes 2 days to get there. If we reduce these by a factor of 2, we're saying it takes 4 days to get there. And let's see what happens. Let's see. Oh, I made a mistake, clearly. Yeah, here. No, it's here. If I make it 4 days, I don't actually delay things very much. I see that, in fact, my decay has gone down. My delay hasn't changed very much. So that didn't actually do what I wanted. So I'll put it back. It's actually a little bit tricky to try to get that delay to work. If I make this number Kc very small, see what happens. Shifts it a little bit to the right, but not much. This is one of the problems with delay equations that I was talking. So everybody was able to get this, where we're now getting a signal in the lymph node. Okay. The next thing that happens is the critical step, the critical delay step, which is that once the signal gets to the lymph nodes, we have replication of effector T cells in the lymph nodes. And so now we're going to actually introduce a new chemical species which represents these effector T cells in the lymph nodes. And we're going to call it EL for effector lymph node. And we're going to assume that the antigen presenting cells, the CLs, convert these inactive T cells into proliferating T cells, and that they also promote the replication of those cells. And so we're going to have nothing goes to EL. Normally, if we have cells replicating each other, the rate of production should be proportional to the number of cells. And we're going to get one term that looks like that, REL times CL, EL. That is the rate of replication of the effector T cells in the lymph nodes is proportional to the number, which makes sense, which would give us exponential growth. But if we start out with EL 0, this would never get started. And so we're going to assume that a certain number of these are produced directly by interaction with the antigen presenting cells. So we have a constant PEL times CL, which is the conversion of inactive cells to active state. And then once they're activated, they start replicating. This would give us an exponential runaway growth. This is a case where we have to ask the question, what happens for large values? For large values, if we have a lot of ELs, the lymph nodes have a finite size. So if we had, we do get swollen lymph nodes during infection, but they don't blow up to the size of the balloon or to our body size. And so we know that there's some limit to how many T cells we can have in the lymph nodes. And so we're going to have a saturation term, which is if EL gets to be large compared to this scale factor K, then our rate of replication saturates. Okay, that's a lot of biology, perhaps. And we have to make some assumptions about how this works. The first thing we're going to assume is that the rate of replication of these cells is about once per day. As I mentioned, about the fastest you could go biologically is about a replication every 12 hours. But once per day is probably reasonable. So the key things we have to know is what's the speed at which we can replicate immune cells. And we'll assume it's about once per day. We have to say how many of these cells we can have. That's essentially, get an arbitrary number. We'll assume that we can have 1,000 of them. And we have to know also how we convert that signal into our starting number of cells. And again, that's a little bit of an arbitrary number because we can rescale everything. We're going to say it's 10 to the minus 4. And so we get a signal that looks like this. The key thing to remember is we're going to get exponential growth followed by saturation. Probably, actually, we should have this go to 0 rather than to a constant. That's something one could play with. And so let's try that and add this term. So why doesn't everybody do that? Add this term. We're going to create these effector T cells in the lymph nodes, and their rate of production is going to be PE1 times the signal that's come in, times their replication rate, times the number we have, times that signal, and we're going to saturate it by this 10 to the third. So we can come down in our notebook. Here's that term. People could try that. And so now let's see what happens to our T cell population. Our T cell population, notice the scale here, it's 10 to the 10th. Our T cell population doesn't do anything for 2 days, so there really is a delay, which is nice. And then it starts going up and it keeps going up. And that's probably not right. Probably, we really should have something where the T cell population saturates. And how could we do that? Let's think about that for a second, see how we could do that. If we think about these things in terms of limits, one way that we could impose that limit would be to have the signal coming from the ODEs, I'm sorry, from the antigen presenting cells go down once we have immune cells activated. And so we could add a term which gets rid of the first part of this, which is going to turn things off so that that first term doesn't keep creating new T cells. See what that does. That doesn't do anything, so that wasn't it. The other thing that we could think about is that let's see what happens in the limit as EL goes to very large. In the limit as EL gets to be very big, we have E1, EL here, divided by KEL plus EL. If EL is very big, this just gives us 1. This whole thing turns into 1. And so we have a constant rate of production, REL times KE1 times C1. So one way to turn this off would be to say that the denominator decreases faster than the numerator increases. And that would be to, for example, square this EL here. And so we could do that. Did that actually not do it? And then I do need to have that saturation. Doesn't seem, nothing I'm doing seems to be making a difference. So I guess I'm guessing wrong today. So that would be good. That would, if we had more time, that would be a good exercise to explore. Would be to try to understand how to get that saturation to happen. At the moment, we're going to live with what we've got, which is we now have a population of T cells in the lymph node that starts out after 2 days and gradually increases and keeps increasing. The next thing we have to do biologically is that those lymph node cells have to come back to our tissue. Once they come back to the tissue, they have a finite lifetime. And so we're now going to write that the lymph node immune cells come back to the tissue. There's a typo here, that E shouldn't be there. And there's going to be some time course over which they come back. Here we're assuming that they come back over a period of about 2 days, and that once they're in the tissue, they live for about a day. And so we're going to add a term now, dE by dt. This is now the immune cells in the tissue are going to be the number that were in the lymph nodes minus their decay rate. And notice there's a balance term because I'm actually actively moving the cells from the lymph nodes to the tissue. So I have a minus KEEL here, KEEL here. So that's going to generate EL goes to E at a rate KE times E1. E goes to nothing. This takes 2 days, this takes 1 day. And why don't you follow that and we can try that. And so now what I see is that I have a spike of immune cells in my lymph nodes, followed a little bit later by a spike of immune cells in the target tissue. Did everybody get that to work? Are people able to get this to run? Yep. Okay, good. Now here you could maybe do the game that I was trying before, which would be to try to saturate things here. And I think this time if I do that, it's going to make a difference. What happens if I do that? Not much, actually. It pulls the T cell rate down a little bit. And if I saturate it here, not much. Doesn't do much. In my experience, trying to wing complicated models is not always the best idea. So now I have gotten most of my cycle. I've sent a signal from the tissue to the lymph nodes. That signal has caused the production of immune cells in the lymph nodes. Those immune cells have now come back to my tissue. And so now that I have my killer T cells, which are these E cells here, back in my tissue, I can have these cells now come and start eliminating my infected cells. But it was a lot of work to do this because we had to go tissue, lymph node replication of cells in lymph node back to the tissue, and they're still not doing anything. Now those cells could come and begin to kill my target cells. And so now I need to think about what those T cells are doing in the tissue. And what they're doing is killing infected cells. And the key thing here, which is going to be a little bit more difficult from our point of view, is that we have to figure out how many infected cells each immune cell can kill. And this is where our discussion of approximation and phenomenological laws started out. Because if we have a lot of infected cells and a few immune cells, then the rate at which we kill is proportional to the number of infected cells, is proportional to the number of immune cells. If we have a lot of immune cells and a few infected cells, the rate at which we kill is proportional to the number of infected cells. If we have a few immune cells and a lot of infected cells, The immune cells are killing as fast as they can. Increasing the number of infected cells doesn't increase the killing rate. And similarly, if we have a lot of infected cells and a few immune cells, increasing the number of immune cells, infected cells, doesn't increase the killing rate because you're limited by the number of immune cells. And so I wrote one possible functional form for this, which was that we have what we call the Michaelis form from before, that the killing rate of the infected cells by the immune cells is proportional to the number of immune cells times the number of infected cells. If there are no immune cells, we're not killing. If there are no infected cells, we're not killing. So we have to have a term like that. And then in the denominator, I saturate separately in the number of immune cells and the number of infected cells. So in this case, if the number of infected cells is very high, the killing rate is proportional to the number of immune cells. If the number of immune cells is very high, the killing rate is proportional to the number of infected cells. And so that has about the right behaviors, although you could argue about whether these should be raised to a power or whether they should be added or multiplied together. And then we have to come up with some parameters for this. And those were pretty well pulled out of the air. Not quite, because we know that, in fact, a T cell takes about 40 minutes to kill an infected cell. That means that each T cell can kill at most 30 infected cells per day. And so that gives us a maximum rate here for killing. And I've picked parameters that work with the numbers that we picked before. And that derivation I'm not going to go through right at the moment. Here, this intrinsic rate, DEI2, I set to be 1/100th, and the scaling constant was 500. If we had an actual experimental measurement of the number of T cells in the tissue, then we could actually get these numbers realistically. At the moment, everything is being fit to the viral load, and that doesn't constrain these parameters. I should say that if we had TJ on the call, he wrote a paper earlier in the year where he did precisely that. He had good experimental data, not on influenza in humans, but on influenza in mice, which had exactly the T cell levels as a function of time. And so in that case, you could actually constrain this model more realistically. Okay, so now we actually have the closed system. It's taken us all this extra work because we had to get the signal from the tissue to the lymph node. We had to produce the cells in the lymph node. We had to get the cells back from the lymph node. And now finally those cells are killing our infected cells and also dying themselves. And so now we have finally the full model of the system, adding this extra term for now the behavior, the appearance and clearance of the immune cells in the tissue, and also the effect of those cells, which is to kill the virus-producing cells. Maybe they should also be killing the latent cells, and we can try that in a few minutes. So why don't we all try that now? You can go down here, and you can now run that full model. Did it run for people? Yes, no, everybody. So now you have the full model, and it's been a lot of work, but we've actually got the shape we want. We have our delay, we have our rise, we have our slow decay, and then due to the immune system, the fast decay. If you look at the picture here, you'll notice that my cutoff seems to be a little shallower than the one in this picture. Although if you look at the error bars, notice at time 8, you have values of 10 to the 4th and also 10 to the 0. So there's an uncertainty of a factor of 10,000 in the viral load at that time. So that's not very constraining on the model, but it's not too bad. And so that really is where this model ends up. We've got the full model in this case, and we could play around with it a little bit to try to make it behave itself better. We're almost out of time, but at least we did walk through the whole model. You can ask the question, how do the parameters that we've assumed to be important here, things that determine the time, when the viral load begins to go down and how fast it's cleared. One of the questions might be, how long does it take the T cells to come back from the lymph nodes? That would be KE. How fast can the effector cells, T cells, kill the target cells? That would be DEI2. How effective is the saturation of, this should be capital K, how effective is the saturation of the immune cell killing? That would be capital K. All of these things will make a difference, and we can play with those numbers and see what happens to the killing efficiency. We could also try to make other changes, and this one is the one that you might want to try right now. What if the effector T cells could also kill the early infected cells? What does that do, if anything? And that's an easy one to do. How would you do that? Well, if we wanted to I'm sorry, I know it's not much fun to watch me scroll, but these are long cells, so it's a little bit difficult to not scroll on them. What we have here is that we have the late infected cells being killed by the immune cells. We could also have the early infected cells being killed by the immune cells. And so how would we do that? Anybody have a suggestion for how to do that?
If we're assuming the same effectiveness by the T cells for the early infected cells as with the later infected cells, then presumably we can just pretty much copy and paste that equation, switching out the relevant actors.
Oh, okay, let's try it. I haven't done it. That was what was suggested here. So let's try it. That would be I2 becomes I1. There, like that. Now this is cheating a little bit. Why is it cheating? From a biological point of view, why is that cheating? Mathematically, there's no issue. You're exactly right. That makes perfect sense. But biologically, why might that not be a good idea? The issue here is that we've said we're rate limited by the number of immune cells. And so if the immune cell is killing an I1, it shouldn't be killing an I2 at the same time. So effectively, by doing this, we've doubled the number of immune cells in our problem. And so we'd expect things to be more efficient because we've effectively doubled the number of immune cells. Let's see what happened. Did it make a difference? Is this actually rerunning? It says it is. It looks like it is cutting off a little bit faster. It's probably not making a huge difference for the following reason. If we look at the cell population, by the end of day 3, there are effectively no I1 cells left. On the other hand, we have essentially no T cells until day 4. And so we basically added, we've said our E cells can kill our early infected cells, but we don't have any of them to kill. And so we actually have added a mechanism that's reasonable. I'm sure it would work, but there aren't any examples of it to happen, so it doesn't do much. What else could we possibly do that might speed up the killing at late stages? To do that, we probably would have to think more seriously about the form here, about how the killing rate depends on the number of immune cells. Perhaps the immune cells are actually more effective at killing than we thought. One way to do that would be to increase the saturation constant. And that would allow the immune cells to kill more effectively. See what happens when we do that. Not much. Another thing that could possibly happen is that the scaling itself could be different. A third thing that could happen is that we didn't get the ramp up of immune cell production fast enough. Maybe the immune cells really turn on faster than we thought they did. And in that case, we could either change the speed at which the immune cells come out of the lymph nodes. That would be KE here. So we could make KE bigger. That speeds things up a bit. So there are a bunch of places one could play with this model. You could argue about details of the model. There's some somewhat questionable assumptions that are made, but it's not terrible, and it does fit the experimental data pretty well. And so the other things that you could try to do, again, trying to change the form of saturation terms we've talked about. You could try to fit different viruses. Everything we did here was based on influenza, and the viral load curves for COVID are very different, for example. They don't have the same shape. And the other thing that would be very interesting to do would be to go out and actually try to see what the number of T cells is in time, so that instead of having some arbitrary guess about the number of immune cells, we actually had experimental measurements of it. And those data are available. And if you have those data, then you can build models that are more accurate. You could ask the question, does the T cell rate look reasonable? Another thing that you might want to think about biologically in this system is that fundamentally what's happening, look at our red curve here, our dead cells. All of our cells are dying in the end. All of our lung cells are dying in the end. We know biologically that that's not the case. If more than about 20% of the cells in your lungs were infected by influenza at any time, you'd die. And so your body's actually pretty good at keeping the infection under control. And so this early cutoff here, where the amount of virus being produced is being controlled by the death of the virus producing cells, may not be right. So that biological assumption may not be right. In addition, at long times, maybe not over the scale of 7 or 8 days, but over the scale of 14 days, new cells are being born to replace the lung cells that died. Your lungs are healing. And so that would make it something like a B SIR model, because we have new cells coming in, born new susceptible cells coming in. So that could be added to the model. We also know that, in fact, not all the cells become infected. And so we'd have to think about, in this kind of model, there's essentially no way to prevent all the cells from being infected. Notice they all get infected very quickly. That's reasonable if we think about a small patch of tissue near a site of infection, but much of the lung never gets infected. And so how we interpret this model and its meaning is something that's it's subtle. I should say that while this specific model, with all the details that I've put into it, is mine, I did it independently. There are similar models that have been published by Perlson's group and people around Perlson, and well calibrated, that reproduce this kind of viral load curve for influenza very accurately. However, when we begin to think about the biology, we have to ask ourselves, is the biology that's represented in the model realistic? We may not care. If all we care about is reproducing the curve and the components are right, that may be enough. If we want to go forward with this and use it for something else, then we do have to ask the question, is the biology reasonable? And of all the things in this model that I would say is the most questionable, the idea that all of the lung cells become infected and eventually die, and that this slow decrease of viral load from day 2 to day 7 is coming about because lung cells are dying, that's not probably a very realistic assumption. So I know that was a bit of a rush, but after weeks of doing a striptease on this, I wanted to walk you through it before the end of the class. And so I appreciate your patience if that was a bit of a rush to get through. But I hope it gives you a sense of at least one full in-host viral model. You've got this exercise under exercise for lecture 10, which you can play with. If you go into the exercise for lecture 11, you'll find a version of this code that has some of these parameter scans in it. So if you wanted to play with that, I understand you've got projects to work on and you probably don't feel like playing with it right now. But if you were interested in that, you've got that code there to play with. As I mentioned, I'm teaching in principle E443 next semester, which is spatial modeling. And we could look at this model in space. And while this model doesn't make a lot of sense as a model of the whole lung, what's going on here does make a lot of sense if we think about a small patch of infected lung. And so taking this model and thinking about and spatializing it works really well. And as I mentioned, TJ just published a nice paper modeling in quite a bit of detail what's happening. In his case, it's not just one cytokine, one antigen presenting cell, and one T cell-like behavior. He actually is modeling all of the different immune species. And he's able to validate that against experiment pretty well. So those are some things to think about. So I hope at least you got to see one model walked through to the end. Are there any questions before we break? Because next week, everyone is supposed to be presenting final reports. I know people have been doing some preliminary, and I'm glad that we see people making progress. But I want to make sure that people have any questions they have answered before we break for tonight.
I don't have much like a particular question, as much as if you're available for it this week, I'd like to meet for an office hours thing.
Great.
To go over sort of what my presentation should look like.
Great, I'd be happy to do that. Send me a message, and I'll get you on the schedule. I don't have my calendar up on the screen because of the way my Zoom is configured. I'll be happy to do that.
Are we going to be filling out like the same rubric again next week, or is that just kind of like preliminary for people to see where they need to improve for next week?
Well, you'd be welcome to fill it out. The only problem is next week I can send it on to people, but they won't be able, it'll be useful feedback, but people won't have the opportunity to use it to improve their talks because it'll have given their talks. So that was why I wanted to try to do preliminary talks so that people could get feedback and use that to improve their presentations.
Okay, thanks. I was just checking.
But however, the reviews of the preliminary, the assignment of going over your partner's presentation in detail is still there. So meeting with whoever you're supposed to work with and discussing their project, that assignment is still there. Next week, if you want to fill out a comment sheet for people, that would be great, but that's not required.